Hi, I'm Daniela Bonus from Math 3D, and for this video we will tackle Chapter 7, Confidence and Interval, and Sample Size. Exercise 7.1 Number 1. What is the difference between a point estimate and an interval estimate of a parameter? Which is better? Why? So the question is difference between a point estimate and interval estimate of a parameter. So a point estimate gives us a particular value as an estimate of the population parameter, whereas the interval estimation gives us a range value which is likely to contain population parameter. If repeated random sample we will taken from population, the point estimate will be expected to vary from sample to sample. A confidence interval will include a true parameter if repeated in sampling. Neither is better. In practice of an interval, it's more useful. A point estimate is something like, I think they will pay you 10 pesos a year. Should a pretty good? An interval is, I believe they will pay you between 5 and 10 pesos a year. That might tell you that there's a lot of variation. So, if an interval estimate is symmetric, the middle point of ordinary supply is reasonable point estimate, but not necessarily the maximum likelihood estimate. This will generate true for positive quantities like standard deviation. Their statistic is better than other. Everything depends on the purpose. Mind you, any and all seems to be subject to some outlandish interpretation. So that's it.
Good day everyone, I'm Maureen Piedades from DSED Math 3D, and we are now in 7.1, which is confidence intervals, and I was assigned to answer one of the exercises in 7.1, that is number 9. Here is the problem. Find each A, Z sub alpha over 2 for the 99% confidence interval, B, Z sub alpha over 2 for the 98% confidence interval, C, Z sub alpha over 2 for the 95% confidence interval, D, Z sub alpha over 2 for the 90% confidence interval, and E, Z sub alpha over 2 for the 94% confidence interval. So, let's start to answer A, which is Z sub alpha over 2 for the 99% confidence interval. By the use of the normal curve distribution between negative Z and positive Z, the area of this region is based on confidence level, which is 99%. So, this area is 0.99. Let's first find the value of our alpha, which represents the total area in both tails of the standard normal distribution curve. So, alpha is equal to 1 minus 0.99 is equal to 0.01. Then, let's find the alpha over 2. Alpha over 2 represents the area in each of the tails. So, alpha over 2 is equal to 0.01 over 2 is equal to 0.005. So, 0.99 plus 0.005 is equal to 0.995. So, we want to identify the z-score given an area of 0.995. So, we need to look for the value of 0.995 in the table, and here it is. So, the value of our z sub alpha over 2 is equal to 2.58. B, z sub alpha over 2 for the 98% confidence interval. By the use of the normal curve distribution between negative z and positive z, the area of this region is based on confidence level, which is 98%. So, this area is 0.98. So, let's first find the alpha. Alpha is equal to 1 minus 0.98 is equal to 0.02, which represent the total area in both tails of the standard normal distribution curve. Then, let's look now the alpha over 2. Alpha over 2 is equal to 0.02 over 2 is equal to 0.01, which represents the area in each of the tails. So, 0.98 plus 0.01 is equal to 0.99. So, we want to identify the z-score given an area of 0.99. So, we need to look for the value of 0.99 in the table, and here it is. So, the value of our z sub alpha over 2 is equal to 2.33. We are now in C, z sub alpha over 2 for the 95% confidence interval. By the use of the normal distribution again, between negative z and positive z, the area of this region is based on confidence level, which is 95%. So this area is 0.95. Let's find first the alpha, which represents the total area in both tails of the standard normal distribution curve. So alpha is equal to 1 minus 0.95 is equal to 0.05. Then let's find the alpha over 2, which represents the area in each of the tails. So alpha over 2 is equal to 0.05 over 2 is equal to 0.025. Then let's add 0.95 plus 0.025 is equal to 0.975. So we want to identify the z-score given an area of 0.975. So we need to look for the value of 0.975 in the table, and here it is. So the value of our z sub alpha over 2 is equal to 1.96. D, z sub alpha over 2 for the 90% confidence interval. By the use of the normal curve distribution between negative z and positive z, the area of this region is going to base on confidence level, which is 90%. So this area is 0.90. Let's first find the alpha, which is 1 minus 0.90 is equal to 0.10. Then, let's now look for the alpha over 2, which represents the area in each of the tails. Alpha over 2 is equal to 0.10, or over 2 is equal to 0.05. Then, 0.90 plus 0.05 is equal to 0.95. So, we want to identify this z-score again, given an area of 0.95. So we need to look for the value of 0.95 in the table, and here it is. So the value of our z sub alpha over 2 is equal to 1.65. And E, z sub alpha over 2 for the 94% confidence interval. By the use of the normal curve distribution between negative z and positive z, the area of this region is based on confidence level, which is 94%. So this area is 0.94. So let's first find our alpha, which is 1 minus 0.94 is equal to 0.06. Then let's look for our alpha over 2, which represents the area in each of the tails. Alpha over 2 is equal to 0.06 over 2 is equal to 0.03. Then 0.94 plus 0.03 is equal to 0.97. So we want to identify the z-score given an area of 0.97. So we look for the value of 0.97 in the table, and here it is. So the value of our z sub alpha over 2 is equal to 1.88. That's all. Thank you and God bless.
Good day everyone, I'm John Saros Picabros from US EdMath TV, and here we have another problem. Unmarried Americans. Nearly one half of Americans aged 25 to 29 are unmarried. how large a sample is necessary to estimate the true portion of unmarried Americans in this age group within 2.5 percentage points with 90% confidence. So, first we need to list our given. We have our P is equal to 0.5. Our Q is equal to 1 minus 0.5 is equal to 0.5. Then we have our Z is equal to 1.64. Then our E, which is 0.025. Since we have this given, we can now substitute it in in the formula for the minimum sample, which is N is equal to PQ Z over E square. So N is equal to 0.5, Q is 0.5, we have our Z, which is 1.64 over our E, 0.025 square. This is equal to 0.25, then 1.64 over 0.025 is 65.6 square. Then this should be equal to 0.25 multiplied by 4,303.36. Then N is equal to 0.25 multiplied by 4,303.36 is equal to 1,075.84. So, with a 90% confidence, a minimum sample of 1,075 is necessary to estimate the proportion of unmarried 25 to 29 Americans. That's all. Thank you.
Hi, good day. I'm Danielle Bonas from Math 3B, and in this video we'll tackle exercise 7.1, number 25. If the variance of a national accounting examination is 900, how large a sample is needed to estimate the true mean score with 5 points with 99% confidence? So we have our given, our variance is 900, and when we score the 900, that is equal to 30, and the 30 is now our standard deviation. And we also have our E, or the maximum error of estimate, which is 5, and of course the Z alpha over 2, which is equal to 2.576. Now you're wondering where did our Z alpha over 2 came from? It came from the given of 99% confident. So let's look at this table. The confident is 99, and we have to find the Z alpha over 2. So the confident level 99% is equal to the Z alpha over 2 with 2.57. So now we have this formula, or the formula for minimum sample size needed for interval estimate of population mean. So we just have to substitute the given. So our Z is 2.576 multiplied by 30 over maximum error of estimate raised to 2. So that is equal to 238.887936, or sample size is 239. That's all. Thank you.